Hello, mic test. Just give me a second, guys. I will check the stream health once if my audio is working fine. Hello, mic test. Okay, everything seems to be working fine. Just give me a second, guys. Yes. So nobody has joined yet, but it's already 7:30. So I guess I will get started. So welcome to this post-contest discussion on AtCoder Beginner Contest 447. This is Aftab Naik, and this will be my first post-contest discussion. So do let me know in the chat if my explanation makes sense, or do I need to be elaborate somewhere, or just any feedback if possible. You can paste it in the comment or in the chat. I will be keeping a track of the chat throughout the live stream. Okay, so the voice is fine. I can see that in the chat. Thanks. So let's get started with the problems. So today we will be discussing the first 5 problems of the ABC contest. So this is the problem statement for the first. I'll just copy paste it. Okay, so the problem statement says there are n seats arranged in a row. Each seat can accommodate at most one person. Determine whether it is possible to sit m people in the seats satisfying the following condition. No two adjacent seats may both be occupied. Okay, so the values of n and m are both very small, and it seems a simple problem, right? So we have been given, let's say, n slots, and in those n slots we have to fill in m persons. But there is one condition, that I have such n slots, no two persons should be consecutive, like they should not be adjacent to each other. So what we can do is we can just place them in alternate fashion, right? Place one over here, then we will skip one position, and then we will jump an alternate position. So using this, we can satisfy this condition. No two adjacent seats may both be occupied. Now, what we have to answer is, can we fill m persons in these n slots in this fashion? So let's do some dry run over some test cases. So first we can have some random values of n comma m, right? Let's do n equal to 4, n equal to 4, m equal to 2, n equal to 5, m equal to 2, n equal to 5, m equal to 3. So let's try to dry run on these 2 to 3 test cases. So let's create slots over here. So 4 slots for this, 5 for this, 5 for this. So when n equals to 4 and m equals to 2, it's pretty easy, right? You can just place them over here and over here. Or you can also do something like this. You can place him over here, or you can also do like first and third position, first or fourth position, or you can do second and fourth position. Anything of it works. So there are various ways to place them, but yeah, it's always possible. So how to actually place them consistently? Like if you are trying to place it randomly and check, then it's tedious. How we will find a simple way which we can guarantee, okay, we will be able to place this all persons. So the first thing is we will try to place them greedily. Never leave the first slot empty. If we have first position, then why not place the first person in the first position? Why to skip this position and move to the next position, right? So whenever we try to place persons, we will start placing them from the very first slot. So here m equals to 2, place it on first slot, then place it on third slot. So here it is also possible. For n equal to 5, m equal to 3, we will do the same thing. We'll place one on first, one on third, and one on fifth. So here we can actually see why placing on the slot matters. Let's say if you didn't place on the first, but instead you went something like this. We went with the second slot, then over here and over here. Now we could only place two persons. But if we started from the first position, then we could place three persons. So to fill the maximum slots, we will always have to start from the first position. So this is the greedy strategy which we will be following for this problem. Now how to find the count? So here we can see if there are four slots available, then we can fill two of those, like position 1 and position 3. If we have five slots available, we will start with 1, we will go like 1, 3, and 5. If we have 6, we will go again 1, 3, 5. So over here you can see like for 5 we have answer 3, for 6 we have answer 3, so for 4 we have answer 2, for 3 we can place at position 1 and position 3, so again we have answer 2. So you can notice a pattern, right? For 3 and 4 the answer is 2, for 4 and 5 and 6 the answer is 3. So this is nothing but the seal of the number. Like if there are n slots, then the number of slots where we can actually place person is seal of n upon 2. So this is actually the solution to this problem. Like if this value is greater than equal to m, then we can place all the m persons. If this value is not greater than equal to m, then we cannot. This is simply our solution. So let's check the code of this particular problem. Yes. So first let's take the input, two integers n and m. Then how many? Okay. So how many solved? Yeah, so today I solved five problems and we'll be discussing those. So yeah, first take input n and m. Then I'm calculating how many max person can I place in this n slots in alternating fashion, which is nothing but seal of n upon 2. Seal of n upon 2 can also be calculated in this way, right? N plus 1 upon 2. Like, let me create a new page. Yeah. So a seal of a number. Seal. So you have multiple ways to calculate seal, right? There is the inbuilt seal function, which many people say don't use it. But if you have to calculate seal of a upon b, then what you can do is you can use a mathematical expression a plus b minus 1 upon b. So this is equivalent to seal of a upon b. And this is integer division, right? This is integer division. So let's say if I want to find the seal of 5 upon 3, which is equal to 2, right? Seal of 5 upon 3. So here I can write it as 5 plus 3 minus 1 upon 2, which is 5 plus 3, 8 minus 1, 7 upon 2. And integer division means we will not have digits after the decimal point. 5 plus 3, 3, 2 are 6. It should be 2, right? 5 plus 3 minus 1 upon 3, sorry. Yeah, a plus b minus 1 upon b. So this would be upon 3 as well. And 7 upon 3 is 2. Yeah. So this is how we take seal. So I have used the exact same method, but since it was n upon 2, I translated the formula as n plus 2 minus 1 upon 2, which goes like this, n plus 1 upon 2. So you can see I have taken the seal over here to find the max count. Then I'm checking if the max count is greater than equal to m. If yes, then I'm printing yes, else no. So this was the logic for the first problem. Any doubts? I guess there is a bit of latency. If you have any doubts, then you can paste it in the chat. For now, I will move on to the problem B. Yeah, so a problem on strings. In fact, three problems today were based on strings. It was a string heavy contest. So let's check this problem out. You are given a string S consisting of English letters. Okay, I will just paste it over here. Okay, so we have been given a string consisting of lowercase English letters. Now remove all occurrences of the most frequent character in S, then output the remaining characters concatenated in their original order. Let's take a string for example. We can take beginner. So let's say this is our example string. Beginner. Now what they said, like first count the most frequent characters and remove all characters with the maximum frequency. So let's just count the frequency of each of these characters. B is 1, E is twice, G is again 1, I is again 1, N is also twice, R is once. So we can see in this example there are two characters with maximum frequency which is 2. So what we have to do is remove all occurrences of E and N from the given string. So I will remove this E, this N, and this E. Then we will be left with B, G, I, R. Is that our answer? Yes. So I guess the problem itself is very easy to understand. So let's focus on the implementation part, how we will actually implement this particular problem. So there are various ways. I will write the overall logic first. First, we will have to create a frequency map. We will have to identify which characters have the maximum frequency, right? So we need to find this frequency of each of these characters. For that, we will create a frequency map, which will be of character comma int. It will find us what is the frequency of each character. Next, we will find characters with maximum frequency, characters with max frequency, and then we will have to erase those, right? So we can store these characters with maximum frequency somewhere, right? We can store them in a vector or we can store them in a set or anything like a map or something. For now, we also need to be able to check like when we are outputting, when I am going through the original string and I am printing my answer, then I will go something like this. First, I will jump on B. I will check if this is a character with maximum frequency or not. Okay, so I need to be able to check very fast if this character has maximum frequency or not. So for that, we need to have some data structure where we can store all the characters with maximum frequency inside it, and we can perform a O of 1 or O of log n check to find whether this character belongs in that set or not. If it belongs, then we will not print it. If it does not belong, then we will print it. So insert characters, insert the above characters into some data structure which will tell us. So a set, and then just iterate upon original string character by character. And if the character does not belong to the set, then you can just print it. If it belongs to the set, then you will not print it. So that's a simple solution for this particular problem. We will we have already performed dry run on this test case. We will just perform a dry run on another test case for clarity. So Mississippi, let's take this particular example. MISSI So let's create a frequency map again. So the first step would be creating a frequency map. So here the frequency of M is M equals to 1, S equals to 4, I equals to 4, and P equals to 2. So this is our frequency map. Then let's find characters with maximum frequency and insert them into a set. So I have created a character set over here. I have inserted those characters with maximum frequency into this set. Now I will again iterate upon this original string. Next I will check, is M a part of set? No, I will print it. I is a part of set? Yes, so continue, skip it. Is S a part of set? Yes, so we will not print it. Again S, it's a part of set, does not, we will not print it. I is also a part of set. S, S, I. We will not print it because they are part of set. Now is P a part of set? No. We will print P. Again there is a P, so we will print it. Again there is a I, which is a part of set, so we will not print it. So this would be our final answer, MPP. Let's check once. Yeah. So this is our correct answer. Let's check code for this particular problem. So here, as you can see, first I have taken the input in a string. Then I have created a map of character comma int to store the frequency of each character. So then I'm iterating upon the string over here. Yeah. So I'm iterating upon the string over here, this particular part. Yeah. Just give me a second. Yes. So over here, we will be iterating upon the string and creating a frequency map. For each character, we will have its frequency stored. Now we have a set over here which stores characters with max frequency, as we discussed, max frequency. And then I will try to find what's the maximum frequency in this map. So I'm iterating upon the map where C is the character and F is the frequency in the map. And I will check if current frequency is greater than max frequency. Then if yes, I will store that current character frequency into the max frequency and I will insert that character into the set. So let's do a dry run of what actually is happening here. So this is like a bit complex way to implement this, but let's go through it. So let's say initially my max frequency was 0. Then I have this frequency map, right? This is my frequency map. So I will be iterating upon this map. So when I encounter 1, F here equals to 1, which is obviously greater than 0. So what I will do is I will erase this 0 and I will set max frequency equals to 1. And I will insert this particular character, which was M, into my set. So let's say initially my set was empty. So I have inserted M into my set. Then I will go on to the next character. So what is my next character? My next character is S. So I will check what is the frequency of S. It's 4. Is it greater than max frequency? Yes. So what I will do is I will change this max frequency to 4, and I will clear this whole set because M did not have a frequency of 4, right? So we are starting fresh because we have encountered a new character with highest frequency. I will store S in this particular set. Next, we will go to the next element in the map, which is I. Then again, I will check the frequency of 4. Is it greater than 4? Current max frequency? No, it's not greater than the current max frequency, but it is equal to the current max frequency, right? So we will insert it into the set, like here in this code. This is our map, and we are exactly checking for this particular conditions. If current frequency is greater than max frequency, then what did we do? We cleared the whole set, inserted the new character, and set the max frequency to the current frequency. So this is the same thing. Clear the whole set, set the max frequency equals to current frequency, and insert the new character into the set. And if it is already equal, then we will not clear the set. We will just insert this new occurrence character into the set. For example, here I. So I already had a frequency which was equal to max frequency. So we did not clear S from the set, but we added I to the set. And then we will move on to P. So when we move to P, we see that the frequency is 2. Is it greater than equal to max frequency? No. So we will just ignore it. It's not of much use to us. So this is how we created our set. I hope this part is clear. Then once we have found out how many max frequency characters are, we have stored all of them into this particular set. We will just iterate upon our original string, and we will check if current character is one of those max frequency characters. If it is not, then we will print it, else we will continue. So that's how we will create our answer, and at the end just print a new line character. So here we are printing all the characters from our answer, and here we'll printing the end line. So that's it from for the problem B. I hope you get it. If there are any issues, please let me know in the chat. I guess there are none, so I will move ahead to problem C. So problem C is also based on strings. Let's take a look at it. Also, I didn't actually went to the time complexity part, so let's discuss the time complexity first. So in the problem, it was given, yeah, this was the problem, and the constants were pretty small. The length of S was pretty small, S equals to 100. And in the first problem as well, N and M were less than 100. So we didn't focus much on time complexity, but let's understand the time complexity of our solution. It's important, right? So as you can see, we have a string. Let's define time complexity in terms of length of string. For example, let's take n equal to size of string, and let's define time complexity in terms of n. So first we are creating a map. So we'll be iterating upon the map and we'll be performing insertions. So for map, insertion is log n, right? And we are inserting n characters. So that would be n log n, n log n. Then we are iterating upon the whole map. The iterating is again n log n, and we are inserting new characters in a set. The set is order set, so it will also take log n for insertion. So basically n into twice of log n. And at last we are again iterating upon the character and checking if it's present in the set or not. So this is also n log n. So n log n, this particular part, this is n into twice of log n, and this is n log n. So our solution would be, if we ignore the constants, the actual value was 2n log n, but since we ignore the constants, our solution time complexity would be O of n log n. Also, you can just replace this map with a vector of int and of size 26, and you can remove that log n factor as well, and it would become linear. But this is a simple problem, right? You don't need to make such optimizations over here since the value of S was less than equal to 100. But yeah, you can optimize it that way if you want. So now let's move to the problem C. So let's create a new page. This is also a problem on strings. The problem says you are given two strings S and T consisting of uppercase English letters. And you may perform the following two types of operation any number of times, possibly zero, and that too in any order. Yeah. Perform following two operations any number of times. So you can do either this or this and any number of times. So insert one character A at any position in S and choose one character A in S and delete it. So what does this mean? Actually, it took me a few minutes to understand. Actually, we cannot just, let's say we have a string S equals to B, C, D, E. We cannot just delete any character from this string. It's not allowed. And you cannot just insert any new character into this string. That is also not allowed. What you can do is, if the string already contains some occurrences of A, then you can delete any of those occurrences or all occurrences of A. Like if you want to delete, you can delete only the character A. And for the insertion as well, you can insert only the character A at any new position. Like select any position at the start, at the end, in the middle somewhere. You can insert anywhere, but you can just insert the character A. And similarly, you can just delete the character A from anywhere. It's not a mandatory operation, but you can do it, and you can do it as many times as you want. So that is the part of question till over here. Now we have to identify whether it is possible to make string S equal to string T. And if it is possible, then find the minimum total number of operations required. So we will be given two strings. Actually, this is the final string. So let us denote it with final. And as you can see, we can only make changes in the string S. We cannot make changes in the string T. It's not allowed. We can only make changes in string S. So what we can do, we can delete any occurrences of A from S, and we can insert A anywhere in the string S. So that are the permissible operations in this particular problem. And after doing those operations any number of times, we have to find if S equals to T. Is it possible? And if yes, then we will have to find in how many total operations is it possible, minimum number of total operations required. So this is our problem. Let's take a test case and see what actually happens when we try to make S equals to T. So let's take a random test case. We'll take A, B, C, and B, A, C. Okay, let's take this particular test case. A, B, C, and B, sorry, and B, A, C, A. So these are our strings. So we can delete all occurrences of A and insert all occurrences of A in the first string, right? So I will just completely erase all occurrences of A from string 1, just for my convenience. I'm trying to figure out a approach. Like there can be multiple approaches. So I'm trying to figure out if I first remove all the occurrences of A and then only insert them wherever they are required. Obviously, it will take some more number of steps, but it will help us find whether the solution, like, can we actually make S equals to T or not? If we have to make S equals to T, then surely it will be possible by this way, right? First, erase all occurrences of A and then only insert A wherever it's required. And then string S should be equal to T, right? And if it's not equal, then we can say it's totally not possible. I will explain this in deep, but for now, my logic is I will erase all occurrences of A and I will insert A wherever it is required. So here there was a which I erased. Now I will insert A, like you can see this B corresponds to 1 to 1. Here this C corresponds 1 to 1. Here A is single, A is missing. So I will add a single A over here. I will add a single A over here. And this way we will have S equals to T. So we have solution. Like this might be one of the possible solution. Erase all A from first string S. Insert character A wherever required. This might not be the most optimal approach, okay? But this is one possible solution. Now let's try to dry run this for another test case. ABC, ARC. So let me write it. A, B, C, and A, R, and C. So my approach was to erase all occurrences of A from the first string. So I will erase this. Now I will insert occurrences of A wherever required. So again, I will insert this A over here. Now I will try to match both of these strings. Are they equal? No. There is one B over here and there is one R over here. And we cannot erase B from the first string or insert R into the first string. So it is not possible at all to make these two strings equal, right? So that is one insight. If both strings have different character at same position, different character at same position, then it's not possible. Then not possible. But we already noticed that we can insert any number of A's either at the front, either at the back, either in the middle. Then will that not change the position of B? And in this simple test case, where it was like there is a single B and C. But what if we had a more complicated test case? Like it was something B, B, C, and we have B, A, again B, and again C. So in this case, B corresponds to B over here, but here B corresponds to A, right? Surely there is B at the end, which will correspond to the current B, but how to handle this number of A's? That is the main part of this problem. That is the crux of this problem. So if we are able to figure this part, then we can surely print our solution. We will be able to find a solution to this problem. So what we can do is remove all the occurrences of A from both these strings. Why am I saying so? Because let's say if our string was ARC and ABC, if I remove all of these characters, because does not matter where A was in the first string or in the second string. For any A in second string, I can surely insert that many A's in the first string and at whatever position I like. So I can perform that operation at the end. Like first, let's sort out the remaining part of the string. Sort out remaining part of the string. By remaining part, I mean string without the character A. String without the character A. If we are able to make those equal, like remove A from the first, remove A from the second, and if we are able to make both of those equal, then for the positions of A which are left, it does not matter. Like we can insert them wherever required and we will have our solution. So first we'll perform a check. We will go through string 1 and we will go through string 2. We'll remove all occurrences of A from both the strings and check if they are equal. If they are equal, then well and good. Then we can just insert A wherever it was required and we will print our solution in minimum number of steps. We'll figure that part. We'll figure out that part how to do it in minimum number of steps. But for now, we are focusing on whether it is actually possible or not. So we can see, like by drawing on this test cases, we could actually see if by removing all the A's from the first and second string, if the strings are still equal, then it is possible. We can do it in some way. But if the strings are not equal after removing all the A's, then it is not possible. And that is the first part of our solution. So the first part is remove all A's from both string S and T. If S and T are not equal after this, then there is no solution possible. No solution. You can just print -1. Now, for the case where it is actually possible. So, I will again try to draw some random test case. Let's consider a three length string like this. I'm writing them a little bit of spaced out. Let's say this was our S and this was our T. This is our S and this is our T. Now, if the final string was something like this over here and this over here. Here we have, let's say we don't have any A's here at all. Here we have one and here we have two. So if this was our final string, three times A, B, then C, then single A, then T, and then double A. And in the second final string, it was A, then B, then twice A, then C, then four times A, then T, then twice of A. If this were our like strings mentioned in the problem, and we can see there is one-to-one correspondence between these characters B, C, and T. To make string S equal to string T, what we need to do is minus 2. We have to remove two A's from over here. Here we will have to add two A's. Here we will have to add three A's, and here we will have to do nothing because two A's were present and we need two more A's. So plus 0. So if we remove all the A's from the original string, then we have gotten like B, C, T in the like after the first step. If we got both the strings equal, then we can easily make this correspondence, right? For B to B, there is one correspondence, C to C, then T to T, and the middle part would get divided into some groups of A like this. In the first string and in the second string as well, there will be some groups between two characters. Like in between these two characters, there is a group of A. Between these two characters, there is a group of A. At the end also there would be a group of A, and at the beginning also there would be a group of A. And it might be possible a group of A like here. Here there was supposed to be a group of A, but it was of size 0. Like there were no zeros, but yeah, we had to add a group of A over here. We didn't actually know, right, how many A's we have removed or added. So initially the size of group of A would have been 0, and we will just calculate. Okay, here it was 3, so write 3. Here it was 0, keep it is 0. Here it was 1. The size of group of A was 1. Here it was 2. And what is the final group of A, like size of group of A which we require? Here we require a size 1, here we require a size 2, here we require a size 4, and here we require size 2. So we can see, okay, so I have to go from 3 to 1A, I have to go from 0 to 2, I have to go from 1 to 4, I have to go from 2 to 2. Isn't that our problem? Like we have to perform some insertions on A, or we have to perform some deletions on A. Here we are performing a deletion, here we are performing an insertion, here we are performing an insertion, here we are doing like nothing. No, we are doing nothing. So by performing some insertion or deletion in string S, we are making it equal to string T. And you can see to make like, is it actually the minimum number? Is it actually in minimum steps? Minimum steps. So you can surely see if there were already two present between B and C, and in the next B and C, in the final string in between B and C, we needed two. Then we don't have to make any change. But if it was 0 and it was 2, then the shortest way possible, minimum number of steps, is to add two characters, right? We'll have to add two characters. If we add three and then remove one, then it will be a lengthier approach. It will require four steps instead of two. So that would be a lengthier approach. But we already have figured out a solution which is the shortest one. Only add the minimum required or only delete the minimum required. And if both are same, then no need to perform any operation at all. We already have figured out a solution with minimum steps. So what we did was first remove all the A's from both the side, then we got a one-to-one correspondence. If both the strings were equal, then yeah, we can in one way or another transform string S into string T. But if they are not equal, then print -1. And to make them equal, we will just calculate the sizes of these groups of A when before like before the start of the string, after the end of the string, and between any two characters of the string. And we'll find these sizes for both string S and string T. So let's say the size of groups in string S was 3, 4, 0, 2, and in string T it was 1, 2, 3, 0. Then how many A's I will have to add or delete? So if the value is decreasing, then I will have to delete 2 A's. If it again it's decreasing, then I have to delete 2. If now it is increasing, then I have to add 3. Now it is again decreasing, so I have to delete 2. So it is actually minus 2, minus 2, minus 2, plus 3. But since all of these are plus operations, like insertion is also one operation and deletion is also operation, so we won't denote them with minus sign. We'll just take absolute of them. Absolute of 2 plus absolute of 2 plus absolute of 3 and absolute of 2, which would result into 9. So that would be our solution. And this is exactly what we'll be doing in the code. Let me show you the code once. Okay, submission. Yeah. So this is our code. Okay. So let's first take the input in two strings S and T. Here I have taken the input. Now I have created two new strings SS and TT. Now SS and TT are the original strings only, but they don't contain any occurrence of A. If the character is not equal to A, then only I will push it into the new string, else I will ignore it. Next, I will check, okay, after removing all the A's, are both string same, the initial string and the final string same? If yes, if no, then it won't be possible to make the strings equal at all. So I am printing -1 over here. And after that, give me a second. Yeah, after that part, so now we'll have to actually maintain the count of groups of A, this particular part. Let's say this was the count of group of A, count of groups of A, groups of A in S. And similarly, this would be count of groups of A for string T. So how to calculate the count of groups of A in string, in any string? Actually, I have created a simple for loop which will help us do that. And I have used the same method for string second. So let me show you that method. So let's say I had a string A, A, B, A, C, D, and A. If this was my string, actually let's just erase this last A, then it will cover all the cases. Initially, I will set the count of A as 0. Like initially my count would be 0. And I will create a vector count A. And initially it would be empty. Now I will go and start iterating upon my string. I have encountered a, so I will increment my count variable by 1. Then again I will jump on second character. Then I have found another a, so I will again increment my count variable by 1. Then I will go to the next character, and when I find, okay, this is not equal to a, right? Then what I will do, I will insert this count into my vector, and I will reset this count to 0. I will reset this count to 0. Then I will jump on the next character. I will see, okay, this character is A. I will again increment the count. So I will go over here. I will increment the count by 1. Then again, I will go to the next character. Here I will see, okay, this is not equal to A. So I will again do a same process. I will insert this character into my vector and reset this to 0. Again, I will jump to next character D. Now I see that it's not equal to A. So again, I will perform the insertion operation. The count value is stored to 0 right now, but still we need to push it into vector, because what this count a vector denotes, it denotes that there is, give me a second, just give me a second, guys. Hello, hello, hello. I'm audible. Sorry for that. Let's continue. Yes. So we were counting the groups of 0, right? Or groups of A, and here we could see that there were no A's between C and D. So we need the count, right? We cannot just say, okay, there were no A between C and D, so we will just skip it. No, we actually need that count between C and D as well. So we will insert the 0. And when at the end, we, we are at the end of the string, then we will again check, okay, now we have finished iterating upon the string. Now, what is the count of A after the string? If there have been additional A's, then we could have just went with whatever the number was. But if there were no A's, then again we need to insert an additional 0, because let's say in the final string it was something like triple A and we got the count 3, and here we will have no element to correspond with this 3A at all. So for that correspondence we would also need to check, okay, if the last character was something other than A, then we will have to push 0 into the string. So that would be our whole logic, and I think this one is right. Let's just count the number of A's. Okay, so initially there are 2, then there is 1, then there is 0, and there is 0. For this particular string A, B, A, C, D, this would be count A array. So we are using exact same method in the solution. Initially we are setting the count variable current A equal to 0. Then we will be iterating upon the string, and for each occurrence of A, I would increment the counter. And if the character is not A, it is something other than A, then I will push the current count into the vector, and I will set current A back to 0. And at the end, I'm again like pushing back that value. Okay, so I have finished the string, and now I need to push back this last value, because let's say if there was D, A. Then we didn't found any other new character. Insertion does not happen upon A, right? Insertion only happens when there is a new character, let's say E or any other character which is not A. Then when I come upon E, then I insert this three value into the vector. But if the string end over here, then we have not inserted this count of three into the vector, right? So regardless of whether the string finished at A or not at A, we'll still push back that particular value into our vector. So I have created two vectors, count S and count T, which will store the counts of groups of A in both of the strings. And once I have both counts, I can just iterate upon those counts and they will also be one to one. I just need to check what is the absolute difference between the group in string S and the group in string T. So as we saw in this particular thing, we have to go from 3 to 1, 4 to 2, 0 to 3, and 2 to 0. That is nothing but the absolute difference, right? So I can just iterate upon those count of A and I can take the absolute difference from both the strings and I will add it to the answer. And thus we will have made both the string equal in minimum number of operations. So that was the solution for C. If everything's clear, then we will move to the next problem, which is the problem D. In fact, I felt that the problem C was a bit more difficult than problem D today. D was quite a simple problem if you were able to see the greedy strategy, and C was a bit on the implementation side. Like you have to find the logic, you have to find the observation on this counts of groups of A. There were some tricky observations to note down. I would say the first thing was probably if someone who don't have much experience with greedy and observations, then how can they arrive at this solution? Like it seems difficult at first glance. Like how can someone think of dividing those into groups of A or to do something or what to do, what to not do, etc. So first thing would be like try various approaches. Try to do anything and everything possible. Or since in the question they mentioned you can only insert A's and delete A's, then try to do absurd things with insertion and deletion of A. So one thing which I tried was insert all A's or delete all A's at the first and insert wherever they are required. So you can try doing this stuff and okay, is this operation taking me closer to my solution? Can I find some more observations? Or if not, I will try to do some another operation or do some another thing, go into another approach. Just try with like take a book, take a pen and paper and try to do operations in different directions. Okay, what if I remove all is from the start? What if I remove all from the end? What if I remove all of them? And just try going on through these approaches and see whether it is taking you somewhere. Are you able to find some observation? So here when I removed all the characters from both the strings, like all the A's from both the strings, then I was able to observe, okay, if in this case the strings become equal, then it is possible to make a solution. But if not, then no solution at all. And after that, again, one observation was how to do it in minimum steps. So I found out that, okay, there is one-to-one correspondence between these characters and I can only insert between them. So yeah, so these were the two crucial observations needed in this particular problem, and this comes with experience. Like since I've solved so many problems, that is one way. Or the second way is just try doing various things. Whatever is mentioned in the problem, just go on trying those things, and you will see some observation. So these are two methods which I usually employ while trying to find observation in the questions. Now let's jump to the next problem. As I said, this was a simpler problem. Also, like before jumping into the problem D, maybe I pasted it. Just previous page. Next. Yeah. So the problem says you have been given a string s. Okay, before that, let's discuss the time complexity of the previous solution. Here's the problem. The size of the string was up to 3 pi, and so let's consider our n as 3 pi. N equals to 3 pi, which is 3 into 10 to the power 5. Just a mathematical notation. And the time complexity of our solution would be, let's go through the code once. Okay, so we are taking both the strings inside our ss and tt variables. We are iterating upon those strings, so it's linear. Then we are comparing. Compare is also linear. Then this whole loop is again linear. For each character in S, we are checking some conditions, and if they are same or different, we are performing some operations. We are also inserting into the vector at the back, which is also O of 1. Similar for the second string. Then we are iterating upon those counts, which would also be linear. So overall, the solution was in O of n. We were not using any advanced data structures or such. We were just iterating upon the string. So that's why the whole time complexity was O of n only. So there was not much to discuss over here. Let's jump to the next problem. So you have been given a string S consisting of 3 characters A, B, and C. Let's take sample input. So here it is A, B, A, C, and B, C, C. A, B, A, C, and B, C, C. So this is our sample string. Now let's see what this operation does. So we have to select 3 distinct indices. Why distinct? Because I is less than j and is less than k. So that means 3 distinct integers. So select any 3 distinct integers such that the first of those indices contains A, second contains B, and third contains C. So let's try to do that particular operation. So I can select 1, 2, and 3. And with this, you can just remove those. Yeah, the remaining characters are packed to the left. We have to remove those 3 indices, right? And we have to find the maximum number of times we can perform this operation. So the operation is select 3 indices, and the indices should correspond to A, B, and C. It's something like BAC would not work, CAB would not work, because it strictly mentioned that I is less than J is less than K, and I corresponds to A, J corresponds to B, and K corresponds to C, as you can see over here. I is less than J is less than K, and I to A, B to J, and C to K. So these are the corresponding things, right? So we will try to do this operation as many times as possible. We have to find the count, how many times we can do this operation. So in this example, we have already done it once by selecting indices. Let me just do the numbering. 1, 2, 3, 4, 5, 6, 7. The first operation, we selected indices 1, 2, and 4. The second operation, we can select the indices A, B. For C, we can either select 6 or either select 7. So let's write it 3, 5, and 7. So now there is only one character left into the string, which is C, and we cannot do the operation anymore. So our final answer would be 2 for this particular test case. Let's check our answer. Yes, our answer is 2. Let's try to dry run over this test case. I will just erase this. The case is CBA and CBB. CBA and CB and B. Now can we select three indices where the pattern corresponds to A, B, and C? Let's start with the earliest A. It seems intuitive, right? Because we hello. Yeah. So it seems intuitive to start with the leftmost character because if we start early, if we start early, then we will have maximum options available. Let's say I select this B, or let's say I select this B. So if I'm trying to pair them with someone, should I select the B at index 2 or should I select the B at index 5? It makes sense to select B at index 2, right? Because in future, whatever options the B at index 5 has, the B at index 2 also have those, but it will also have these two options in the middle. Like this will correspond to this C, but there is no C ahead. So it always makes sense to start as much early as possible. If you do that, then you will have the maximum options available and you can perform, like you can select the maximum number of pairing. So that is one greedy strategy which we will be using here. This is similar to the greedy strategy which we in the first problem. We were always starting like, at the first position. If there are n slots, then let's start placing them from the first slot itself. Why waste a slot when you have it available? Why start from 2 when you can start from 1? Similarly, why start from 5 if you can start from 2? Because 2 will give you all the options which are available for 5 and also all the options which are between 2 and 5. So always start early. That is one key observation which will help us solve this problem. Other than that, are there any observations? What we can see? This is one. Okay, for any character, if I am selecting any A, just select the first A and then try to pair it with the earliest B. Then try to pair it with earliest C. This will help us in like to form maximum number of pairs. Rather than selecting A which comes much later, we'll go ahead and form the pair with the earliest possible option. And we also know that if I have already selected A, then there is no point in selecting another A, right? We will have to select B for the next and then C for the next. And we cannot jump from A to C directly. We need a B in the middle. So this is one observation. Next, okay. So create one more page and take another test case to dry run. Test cases in this problem are not that good to give some decent understanding. So let's just go with this particular test case. A, B, C, and again A, B, and C. In this problem, you can go with start with this A, select this P, and go to this C. Sorry, go to this C, or you can start with this A and B, and you will only form one pair. So this also showcases that if for this particular B, we already have some C available earlier, then take that option. Because if you take that option, then this C would be available for some other pair of string in the future. So not only like pairing for the earliest ones helps like find more options for this C. Earlier our logic was for this particular C, uh, like for any, if I select a B from here and B from here, then this B will have so many options to pair. There can be a C over here, but there is no C anywhere. So if I select this B, then I will not be able to form a pair. But if I select this B, then this B and this C together can form a pair. So that was one of our logic. Like this is one reason why we'll have to like we'll try to select the earliest possible character. But in this case, you also saw that if for this particular B, if I try to select this particular C, then we already had a C, but we deprived another pair of this C. Isn't that decrementing our answer by one? So that is actually reducing our options. So by for these two reasons, we will always try to pair them with the earliest possible characters. So that would be our greedy strategy. Start with A, find the earliest next B, and for that B, find the earliest next C. If we find one such tuple, then we will increment our count by 1. So that would be our answer. Now we'll have to exactly simulate this in our code. So for that, what we can do is, let's say initially our string was A, B, C, A, B, C, and A, B, and C. In this case, we can pair this one, and from here we can go to this. Then we can pair this one, and for this AB we can go to this, and for this AB we can continue with this, and we will have 3 pairs. So this is our solution. First take A, then B, then for that B find the next nearest C, and then we will increment our count by 1, then again go on to the next pair A, B, and C. But if we will have to find a better implementation for this solution. One solution is just go iterating upon the string while some answers are possible. I will try to find one occurrence of A, then B, and then C. If I found them, I can just write them as 0, 0, and 0. Then again I will start iterating upon the whole string, then find the first occurrence of A, then B, then C. Then I will again replace them with 0, and again I will go on to the next iteration, then again go find one tuple and create 0. So the time complexity would be something like n upon number of pairs. This linear loop will run for n upon 3 times because that's the maximum number of tuples, right? So this would be a n square on 3 type solution. But we don't want that. We want something better, right? So we can definitely optimize it to a linear time solution. Let's see how. So take that exact same test case. A, B, A, B, C, A, B, C, and again a C at the end. So we know that a single A can pair with B and a paired AB can paired with C. So if at any moment I have the count of A, if I know okay these many A's at current index I have these many A's and I have encountered a B, then can I not create a pair of AB? I will just take one A from here and I will take one B for like from the correct position and I will create a pair AB. And similarly, if I have count of pairs of AB, like if I have count of pairs of AB till index I, then if I'm on a random index and the value is at C, then I can take one pair from over here and I will take one C from over here and I will create a tuple of ABC. Isn't that possible? And we will just have to count number of tuples of ABC which we can create. So we can see if we maintain the count of A, if we have the count of AB, then we have count of A, we have count of AB, and we have count of AB. Then we can find the count of ABC, which is actually the solution to our problem. The problem says find the number of tuples ABC which we can create. So if we find that count of ABC, then that's our solution. So we will just do what we did over here, the same thing. We will keep some variables, count A, count AB, and count ABC. So first, let's go over here. We see, okay, we have a over here. So I will increment this count A with 1. Initially, this will be 0. Next, we jump to B. Now we see, do we have any A behind this B? Okay, we see count A is 1. That means, yeah, we actually can make a pair AB. So we will take 1A from this count A, will decrement it by 1. So it will go to 0. And this count AB would actually go to 1. We will have this A second. Yeah. So next we have again character A. Now for A, I will just increment the count of A by 1. So it would go like this. Next, I encounter a B. Then I see, okay, I already have a A. I can use that A. It will go to 0 and I will increment this count by 1. Now we have two pairs of AB ready and count A is
So
0.
this is the main condition. So what we'll do simply is, simply count the count the frequency of all the elements in N, and you have calculated the sum. Now simply calculate the frequency of all elements in sum and check like whether these two frequencies are equal or not. So this will be our approach. So let's see.
Yeah, sorry for that. So we were on the counting step, right? Next, we will jump to character at index 5th and we see, okay, this is a C. Now we have found a C. We will check for number of pairs of AB. We have 2. So what we can do is take one pair from AB and take this C and pair all of them together. So this 2 would go down to 1 and this 0 would also go to 1. Now we have one pair of ABC, one AB, and count A is 0. Next we will jump to A. Again it will go like count A would be incremented to 1. Then we will have a B. So this one would again go back to 0 and this would go back to 2. Then we have a C. So we will use this C with one of the AB. It would go back to 1 and count ABC would increment to 2. And again we have a C. We will again try to pair it with some AB. So it would decrement to 0 and this would increment to 3. So in this way, we have found 3 tuples of ABC. In this case, like all the characters were part of some or the other tuple, but what if they were not part of some or what will happen when they are not part of this tuples? So we'll just use a simple test case over here, A, B, C, and do this. A, B over here. So over here we will again dry run the same approach. I will have count A, count AB, and count ABC. let's start from here. Here I will have count 1. When I go to index 2, this would increment to 2. Then I go to B, this would decrement by 1 and this would increment by 1. This was 0, right? When I go to C, I will use this AB pair, decrement by 1, and this would get incremented to 1. Now when I encounter B, I will make a pair of AB. So this will go to 0 and this will go to 1. So the final state would be count A is 0, count AB is 1, and count ABC is 1. So we are able to form only one tuple of ABC, this particular case. So that is our solution for this particular problem. Let's go through the code once. Hello? Yeah. So let's go check the code. So I have maintained same three variables, count A, count AB, and count ABC. And then I'm iterating upon the string for each character. If the character is A, then I'm incrementing the count of A by 1. Else if the character is B, then I'm checking, okay, does there exist any A behind this B which is not already paired? So that is denoted by count A. If count A is 0, then I cannot make a count AB pair, like I cannot increment the AB pair, right? So first I will check if the count A is greater than 0. If it is greater than 0, this condition, if count A, this means count A is greater than 0, then I increment the count AB by 1 and I decrement the count A by 1. And then similarly, if the character is C, like if the character is A case is over here, the B case is over here, in the else case, it would be C, like character is C. So if count AB is greater than 0, then I can use one of the previous AB pairs with current C and I can form a tuple ABC. So I would increment the count ABC by 1 and decrement the count AB by 1. And in the finally I will print the count of ABC as my solution. So this is the solution for problem D. Talking about the time complexity, we are iterating upon the string only once. So if the length of the string is n, the solution is linear in time complexity. So that was the solution for problem D. Now let's go to the final problem of the day, problem E. So the problem says you have been given a simple connected undirected graph G with n vertices and m edges. Okay, so let me just copy paste the problem statement. You are given a simple connected graph, simple connected undirected graph. So that means the whole graph is connected. It is not like there are separate components. Okay, the whole graph is connected. So something like this. And the edges are not directed, they are undirected. You can travel in both the directions. There are n vertices, m edges, a standard setup, and there are at least two nodes. At least two nodes. Okay. And we have, and the edges are numbered from 1 to m, and the vertices are numbered from 1 to n. It is a one-based graph. The edges are also one-based. Edge I connects the vertex ui and vi. Each edge has a value called a cost, and the cost of edge is to the power I. Okay, if there are three edges, 1, 2, and 3, cost of first edge would be 2 to the power 1, second would be 2 to the power 2, third would be 2 to the power 3, and the ith edge would be 2 to the power I. So this is the cost associated with each of the edges. You will now choose some edges of G to delete so that the number of connected components of G becomes exactly 2. It can be proven that this is always achievable under the constraints of this problem. So initially there was a single component. Let's draw this graph. So initially there was this graph, can be like this or any. Yeah. So let's say initially if this was the graph, so we have to delete some edges. We can delete some edges, and after the deletion of those edges, the number of components should reduce down to 2. Currently, the number of component is 1, right? This whole thing is connected. So this is one single connected component. But they want us to delete some edges and make the graph such that there are two connected components. So in this case, what we can do is delete this edge, and this edge. This way we will have two components. The first component would be something like this, and the second would be the remaining part from here to here. So we have to divide the original single connected component into two components. We will, so that is one part of the problem. For single connected component, we have to delete some edges such that the number of components becomes twice, and then we have to find minimum possible sum of cost of deleted edges. So let's say if I deleted this edge, and this edge, some edges of G to delete, so that the number of connected components of G becomes exactly 2, and find the minimum possible sum of cost of the deleted edges, so that 998248. So here we have to delete the edges in such a way, delete in such a way that sum of deleted edges is minimum. So this is our problem statement. Select some edges to delete. Let's say I delete these three edges. After the deletion of these three edges, the sum of these deleted edges is minimum, and the graph is divided into two components. I could also have selected some other edges, like let's say if I deleted this edge, and this edge, then this two would fall into one component and rest all would fall into another component. So there are various ways in which you can divide the graph into two components, but since the weights of the edges are strictly increasing and they are also in power of 2, so that introduces us to an amazing property which I will cover. But for now, we can see that there are multiple ways to divide the graph into two connected components, and we have to delete edges in such a way that the sum of deleted edges is minimum. So we will try to do that by deleting the minimum number of edges. Like you can think, if I have to keep the sum of deleted edges as minimum as possible, then the two things which comes to the mind are, first we can delete as few edges as possible, so this is the first approach which will come to the mind. Like if you think, okay, I want to minimize, delete as few as possible. Less the number of edges deleted, less is the summation. So that is one thing. Or the second thing which we can do is, even if edge count is higher, even if edge count is high, then select ones with minimum weight. So these are the two observations, or you can say strategy, which comes to mind. Either delete as few edges as possible, or if we like, if there is a way to select three edges and then we are able to divide the graph in two connected components, and there is another way in which we will have to delete six edges to divide it into two connected components. Then the first thing that comes to mind is select the lower one. But this is actually wrong. This is intuitive at first glance, but if we, I will show you a proof or a test case that this will fail, and I will also show you the reason why. So these are the two ideas which we will work upon. So first, let's go through this approach. Why deleting as few edges as possible might not be the best option always. And then we will come back, even if edge count is high, like delete, we are deleting more number of edges per the original sum, like combined sum of all of those would be minimum. So let's try to come up with a graph. Okay, so they have given us a graph. So this is one. Which one should we take for the example? Let's try to take this itself. This is not that interesting of a graph, but still. Okay. So in this particular graph, okay, initially these dotted lines are also connected. Okay. So these were also connected. They were also given as a part of edge list. This was edge 1, 2nd, 3rd, 4th, 5th, 6th, and 7th. So the corresponding weight of these edges would have been 2 to the power 2, 3, 15 over here, 32 for this edge, and 64 for this edge, and 128 for this edge. So these were the this would have been the corresponding edge weights, and they deleted some of these edges. So they deleted the edge with weight 4, and they deleted the edge with weight 2, and the edge with weight 16. So they deleted these three edges, 4 plus 2 plus 16, which will be 22. So the sum of cost of deleted edges in this test case is 22, and they have explained it in the solution. Deleting edges 1, 2, 4, the edges shown as the dashed line in the figure above, makes the number of connected components exactly 2, and the sum of deleted edges is also the minimum. So this is the only way where we can achieve the minimum sum. The components would be this. 2 and 4 would fall into the same component, and 1, 3, and 5 would fall in the same component. So these would be the two same components, like two disconnected components in the graph. So I think the problem is clear to everyone, right? What we have to do. We have to delete some edges and keep the sum of those edges as minimum as possible. So I will introduce a new concept over here to solve this problem, which is MST. Now people will say minimum spanning tree, but no, I'm actually talking about maximum spanning tree. So what is a minimum or maximum spanning tree at all. So first cover this problem. What is a minimum spanning tree actually? So let's say there are n cities direct shown as a graph. Let's say these were the roads in that five cities. These are the five cities, and you have to maintain these, okay? Like you have to maintain each of the road, but you are lazy or you don't have sufficient funds, and there is a cost C1, C2, C3, C4, C5, and so on. Like each age is associated with some cost. Then ideally, you should keep all the pathways, all the roads in good condition so that you can go to any city from any city, whichever route, like you can select any route and you can go from any city to any other city. But if you are constrained on the total money, let's say you can only provide funds up to K or whatever, then you will still have to keep all of these cities connected, right? Let's say there was a direct route and was a indirect route through this. Like you can go from here to here, from city A to B to C, or you can go directly to city C. So instead of maintaining both of these routes, you will only just maintain one route. If you maintain A to B and B to C, then you have A, B, and C, all of those are connected, and you won't have to pay the cost to maintain this extra road. So what you are actually trying to do is create a minimum spanning tree. Like find the minimum number of edges, like minimum cost edges, and after placing all of those edges, you will have a single connected graph. From any node, you can go to any other node. Like you can select any node and you can go to any other node in this graph, and that too at minimum cost for whole graph. That is the minimum spanning tree. So here, despite we are having like pi into n into n minus 1 upon 2 edges, we don't need to maintain all of those edges. We only need to maintain n minus 1 edges. It can be proven that using n minus 1 edges, you can connect this whole graph in a form of a tree. And that n minus 1 edges should be of minimum weight, such that the sum of the cost of all the roads would be minimum possible. But in this particular problem, the question is the exact opposite. What you have to do is you have to delete the ones with the minimum cost and keep the ones with the maximum cost. So one other thing which changes is, let's say earlier you had a graph like this, and if you wanted to create a minimum spanning tree of this graph, you will try to delete as many edges as possible. I will delete all of these edges between the middle. Like I will try to keep only the minimum required edges. But if I want to create the maximum spanning tree, I will try to keep as many edges as possible. जितने रखते आ रहे उतने रख दो, ये भी रख दो, ये भी रख दो. I will try to keep everything. But there is a constraint in the question. Like if I want to create a maximum spanning tree, like this concept does not exist, because what does a maximum spanning tree means? Just take each and every edge. Because if you want maximum, then why ignore any edge at all? Just keep all the edges. But in this question, they have introduced a condition that the number of connected components should only be two. So if I am keeping all the edges, then the number of component is only one. So I will have to delete some edges and the make the number of components equal to 2. So we will use the same algorithm as MST, but we will tweak it to find the maximum spanning tree. So what MST does is, since we want to find a network, by network I mean a graph, we want to find a network with minimum cost. Minimum cost. What we do is we just place all the edge, nodes initially. Let's say node 1, node 2, node 3, 4, and 5. And we don't place any edge right now. Then we take all the edges. Let's say there are 6 to 7 edges. 1, 2, 3, 4, 5. And the edge number is also the edge weight. And they connect. I will also put names A, B, C, D, E. So we have, let's say, 5 edges: start node, end node, and cost. U is the start node, W is the weight, and V is the end node. So let's say I have the nodes. Okay. The first edge connects node A and C with the cost being 3. The second connects C and E with cost being 10. Third connects B and D with cost being 4. And then we will have A to E with cost being 1. And we will also have another edge. Let's say we have an edge from C to D with cost 100. Okay. So if these are our edges and we want to optimize for the minimum cost, then what we can do is initially don't place any edge, sort all the edges in ascending order of their edge weight 1, 3, 4, 10, and 100, and then try to connect those edges. First would be AE, second would be AC, third, fourth would be BD. So 1 with 10 is CE, and the last is CD. So I will first place AE on the graph. Since this is the minimum edge weight, we will it's like a greedy plus mathematical type of setup where choosing the minimum edge. If A and E are not already connected through some path, then it's always best to connect A and E through the shortest edge weight possible. So that is our whole logic. Next we will go to A and C will connect A with C. Next we will go B and D like this. Next we have C and E. They are connected. Okay, they are already connected with one path. So don't connect them again with another path because that would just introduce some more cost. Then we have C and D. So you can prove that this is the minimum spanning tree of this particular graph. It always works. This is the Kruskal's algorithm to finding minimum spanning tree. Now we will tweak this. Instead of sorting the edges in ascending order, we will sort them in descending order for our problem. Because they said to delete the edges with minimum weight. So what does that mean? It means keep the edges with maximum weight, right? So this is what we will do. We will create a graph. We won't place any edges as of now. We will take the edge list. We will sort it in decreasing order. Decreasing order. Initially, the number of connected components would be n as the number of nodes. Initially, the number of connected components would be n, right? And when we merge two nodes, they will combine into a single component. And this will happen until there are two nodes, like two components remaining. So we will sort the edges in decreasing fashion, then pick a edge and see if number of connected components is greater than 2. If it is greater than 2, then we will just continue. But if it's equal to 2, then we will have to stop, right? This is the condition. Like if it is equal to 2, then we'll have to stop because we can't let the number of components decrease less than 2. And when does the number of components decrease? The number of components decreases when we connect two nodes U and V which are not in the same component, right? If I connect one component from this node and this node, then these both will now be a part of single component. So I will have to stop when the number of component is 2 and there are two nodes u comma v which are in different components. So at this condition I will have to stop, but until then I will just keep on selecting an edge and add them. Select a edge with maximum weight, add it to the graph. Select a edge with maximum weight, add it to the graph, and continue until the number of connected components is 2 and both u and v are in different components. So if I add that particular edge, then the number of components will decrease down to 1. So using this strategy, we can create a graph where edges have sum of edges is maximum, and that means like that also means sum of removed edges is minimum, which was our problem, minimum. These both things, like if this is true, then only this is true. It cannot be like one is false and other is true, because they are opposite sides of the same coin, right? If I am creating a graph where the sum of edges which I have kept is maximum, then the sum of edges which I have removed would be minimum. So both are one and the same thing. And this was asked in the problem. This was asked in the problem, and we are looking at the problem from this angle. Create a graph where edges are maximum, and this was asked like sum of removed edges is minimum. So we will solve this problem because as we saw, these are the same sides of a, like these are the different sides of the same coin. So if you solve this problem, then this problem is automatically solved, and we can just output this particular thing. So our solution would be like as we saw over here. First, take the edge list, then sort them by decreasing order. And while this condition is not satisfied, you can just keep on adding the edge to our graph. So that is our solution. Let's take a look at the code once. Yes. So this is the code for efficiently finding whether two components lie in the same, like two nodes lie in the same connected component or not. We need a data structure called DSU. Like if you ever try to find MST or stuff, you might be knowing about DSU, right? Because this operation of checking if U and V lies in the same component or they lie in the different component, this is a problem in itself. This is a classical problem which can be solved using DSU. If you don't know about DSU, then it's fine. You can just learn about it. But without DSU, actually, you can't solve this particular problem. So you can just stay for the logic part of this problem. So this is my DSU. Let's understand this at a high level. DSU has two like important functions: merge two nodes. If two nodes lie into different components, then it can merge those into a single node, and it can also tell us whether two nodes lie in the same component or not. So that is the, like if you want to use DSU as a black box, then it can find us two things: merge two nodes, find whether two nodes are in same component, in same component. And this is done in alpha of n. Let's not talk about alpha, just say that this is smaller than log n. Is smaller than log n. Login works, right? And this is smaller than login, so this also works. So we will be using these two ideas from DSU as a black box. So first I'm taking the input into an adjacency list. Then I'm taking all the edges as the input. The edge is like weight, comma, start node, comma, end node. So I'm storing it like that. Integer array of three. The first would be the weight, the second would be the start node, the third would be the end node. Then I'm pushing back all the edges into the vector. Then I'm sorting them into reverse order. You can see R begin and R end, right? So I'm sorting them in reverse order. Then I'm initializing my DSU with n plus 1 nodes. And comp is my component count. So initially my component count would be n, as we saw over here. If there are n nodes, then initially there would be n components. And if I combine all of those, then it would ultimately reduce down to one component. But we have to stop when the number of components is equal to 2. So that is our problem. So I will iterate upon all of the edges. If component count is 2, then I would stop. Else I would take that edge. I would check, are they in the same component or not? If like U and V are in different component, then I would just merge them. Okay, I see. The component count is greater than 2. Like there are 3 components, but I want only 2. Then I will merge U and V. If like let's say there was another component, then it's totally fine if we reduce the component count by 1, right? So if U and V are indifferent, I would just merge them. And I would do a component count minus minus, and this loop would go on. With this, we will have created our maximum spanning tree. Next, I will sort all the edges, and after sorting all the edges, I will go and check. Okay, now I have to find, after creating the maximum spanning tree, I actually have to find some of edges not added to the graph, not added to the graph. So what does that mean? So that is actually saying, okay, this will help me find the edges which I have not added. Because if I already added some edge, let's say if I already added some edge, then that means if there is a edge between A and B, then that means A and B will lie in the same component. If there is edge between C and D, then that means C and D lies in the same component. But if there is no edge between A and C, then that means A and C lies in different component, different component. So there should not be any edges from this component to this component. Rest all edges, they are valid. Here also these all edges would be valid. Just we will not be including edges from this component to this component like this. So just don't count these edges. So that is what the code does. It iterate upon all the edges. It checks, okay, are the edge in the same component, U and V? If they are not in the same component, if they are these green edges, that means we have not added these edges. We have deleted these edges because this will result into the minimum sum of the removed edges. Then we will add that edge into our answer. And again, you can see we have sorted the edges. So edges would be like this: 1, 2, 3, 4, 5, and their edge weight would be 1, 2, 4, 8, 16. That is just a multiplication of 2, right? I'm doing the same thing over here. Instead of writing for int I equal to 1, I is less than equal to m, I plus plus, I'm just maintaining the cost value. Initially, the cost would be 2. As you can see, the cost of first stage is 2. Like actually, this is not 2 to the power 1 is 2. This is 2 to the power 2, 8, 16, and 32. Yeah. So if they are not in same, then I would add that value P into the answer, and I would just proceed. And at each run, I would multiply P, means the current edge cost, by 2. That is what I am doing here, right? I'm multiplying the cost by 2. And if, let's say, if this edge was not a part, these two edges were not a part, then I would just add this cost into the answer plus equal to, and I would also add this part into the answer. So that is how we arrive at our solution. So this was the whole solution from the problem E of today's contest. I hope you get this solution. If there are any doubts, please let me know in the comments and I'll be sure to clarify. So now let's go through the time complexity of this code. And also I have not touched the modulo aspect of this problem, because as we can see, m can go up to 1e5, and the edge cost then can be 2 to the power m, which is 2 to the power 1e5, which will easily exceed the 1e18 limit of long long. So that's why we will store all values in modulo. Like, we will keep our answer modulo something. I hope you know this stuff. So we are using a different modulo over here. The modulo is 9982445353. Make sure to include that in your answer, else your answer will overflow and you will get a wrong answer on hidden test cases. So let me just show how to take the modulo once. So in this problem, I have defined the modulo at the start over here, and whenever I'm adding something to my answer, or when I'm calculating a power of 2, for example over here, when I'm calculating the power of 2, I multiply the current power by 2 and take it modulo. And similar, when I'm adding P to my answer, I first calculate the sum and store it modulo the mod into the answer. By doing this, I make sure my answer does not overflow. So that is the solution. Now let's go through the time complexity. So if we go through the code, what we are doing is, first we are creating the adjacency list, then we are sorting, like, we are creating the edge list, then we are sorting the edge list, which would be m log of m. Yes. How to come up with such logics during the contest? Uh, Pranit, are you talking about problem E, or problem D? Could you clarify, you are talking about problem D or problem E? Till the time he confirms, I will just proceed with the time complexity part. So first we are sorting the edges. So the sorting time complexity would be m log m for m edges. And next we are initializing the DSU. Initialization is in O of n. Then we are iterating upon all the edges. And for each edge, if they are not in same, we are merging. Both of these operations are performed in alpha of m. So iterate upon all m edges, and for each edge we will perform alpha of n, and it is a small value, something like 5 or 6. Okay, so this loop will cost us m into alpha of m. Next we are again sorting the edges, which is m log m, and next we are iterating upon the edges, and we are again checking if they are in the same or not. So this is again alpha of m. So since alpha is like really small, up to 5 and 6, this will be the dominant part of our code. But to denote it accurately, we can still write it as m log m plus m into alpha of n. And many people like use log n here as well, but this is the more accurate representation. So this would be our solution time complexity. Uh, okay, Pranit, you were talking about problem E, right? So how to come up with this particular approach, or for any problem, how to come up with approach. So what you can do is go through the problem step by step. Like if you check this first slide over here, you can see that I was going through the problem and highlighting all the important parts. What type of graph it is, how many number of nodes are there, is it zero based, is it one based, what is the cost of each edge. Now, there are some more important facts in this statement. We have to choose some edges of G to delete, and then number of connected components of G should become exactly 2. Then these are the important stuff which you have to note down. Once you have noted down this stuff, then what you can do is find the invariants. What does invariant mean? Find the invariants in the problem. Find the invariants. So what is an invariant? Invariant means the problem stays the same. Like there are some things in the questions which changes, and there are some things which does not change. Does not change. So you have to focus on that particular part. For example, in this question, okay, in this question, when I reframe this particular problem, create a graph where edges is like sum of edges kept is maximum, which is similar to sum of removed edges is minimum. So I rephrased the problem, but the invariant of the problem was same, right? Sum of removed edges is minimum here as well and here as well. So this was the invariant. Now, how did I actually discover this? It was logical to think, right? If this particular part again, delete as few edges as possible. This is the first thing that comes to mind. And the second thing which comes to mind is even if edge count is high, select ones with the max minimum weight. So the overall summation is minimum. So try to think of many changes in some or other part of the solution. Figure out some approach, and like I said, these were the two approaches that came to my mind. And then intuitively, I went with the thing, okay, is it so if I create a graph where edges is maximum, then sum of edges removed would be minimum? Because most of the times they won't present you the question directly. They won't, they won't present you the question directly, right? Directly. This is like very useful, and most of the times they do this. They won't present the question directly. In fact, there is some algorithm to solve one problem, and they will ask you exactly inverse problem. Inverse means they will ask you the exact opposite question, and then you will have to decode that question into the original question, solve it using the algorithm, and then from the original answer calculate the inverse answer and then print it. Similar thing happened in this problem, right? So we were asked to find the sum of minimum edges, but the problem could have been solved with maximum spanning tree. So maximum spanning tree type of idea already exists, right? In fact, they might have first created the solution, and then to complicate the question, they might have inverse, like framed the problem in an inverse way. So instead of asking, find me the sum of edges, like if I kept maximum number of edges and the component is 2, then find me the solution. That would have been very easy because then we know the minimum spanning tree exists and we might have solved this. But by framing this problem into its inverse side, they have made the decoding part of the question difficult. So try to see the question from another angle. So if they have asked one thing, what is the opposite of that thing? Can I solve that opposite thing using some algorithm? Or even the question itself, can I solve the given question directly using some algorithm or the opposite thing using some algorithm? And most of the time, if it is one way or the other. So that is one thing which you can keep in mind. The question might be inverse of something, or there might be some things which changes in the problem. There might be something which does not change. So focus on the things which are not changing, and try to find observations among those things. That is one way to find these observations. Also, one thing would be, since this is a graph problem, the graph section is pretty limited, you know. They have some fixed number of algorithms. Let me show you. Yes, yes. Yeah. So this is the CSS graph section. There are some handful of problems. In fact, I have not solved most of them. But the initial like 20, 30 problems, if you solve those problems, there are a finite number of ideas in graphs. So if you have done all of these problems, you know specific algorithms exist for specific set of tasks. Like I talk about MST over here. Then there is shortest path. There are various ideas for shortest paths. There is binary jumping. There is topology sort. There are some other ideas as well, but there is like finite number of ideas. So whenever you see a graph problem, you can just go through this checklist. Can this problem be solved with MST? Can it be solved with shortest path? Can it be solved with binary jumping by topological sort, and so on? And while going through this, you might be able to frame the problem in one of these algorithms, and maybe you have find your solution. Like there are some more. So one other advice would be, have some variety under your belt that will help you identify a problem quickly. So that would be my advice to solve graph problems or find observations in graph problems or in general problems efficiently. So are there any other doubts for today? I think there are no further doubts. So we will end this session here. Thanks for joining everyone. Have a good day. If you have any further doubts, please let me know in the comments. Also, since this was my first post-contest discussion, feel free to leave your feedbacks. Thanks for joining, Pranit. Thank you, guys. Please leave your feedback in the chat. How you felt like could have. Should I slow the pace? Should I increase the pace? Or maybe some suggestions from your side, open-ended suggestions, and I'll be sure to incorporate those in my further sessions. Thank you all.